Alright, so today I'm going to expand on the topic of heat, and we're going to start with expanding on the topic of conduction and insulation that I talked about a little bit earlier. So you have a cake. You go, you bake the cake. You pull it out, and you forgot to grab oven mitts. So you grab it by the tin, and you scream because it's hot. And the reason for this is because the tin is metal. So the heat transfers to your hand very fast because metal is conductor, so heat transfers through conductors very fast. But the cake, when you touch the cake, it feels nice. Why is that? Because the cake is an insulator. And it doesn't transfer that heat very well. But what's interesting about it is they're the same temperature. Like, the exact same temperature. And you can test that. I don't have the capabilities because I can't bake. No, I'm kidding. I just don't have the time right now. But, we'll have to take my word for it. But say we have this, well, piece of hot thing, and you put it in cold water. Hot thing is 75 degrees. Cold thing is 25 degrees. What's going to happen is, even though this hot thing, we're going to say it's iron because conductor and insulator, we're going to stay on that. Or, yeah. No, water's not really an insulator, but yeah. They will reach thermal equilibrium. Beautiful drawing here. To where they are both 50 degrees. Or because of energy, like it's steaming off here when the iron gets dropped in. So thermal energy may be lost here. So they may be 49 and 49. But they will be the same eventually because of thermal equilibrium. So we're going to go back to our cake. This cake is the exact same. The cake and the tin are the same heat because of this thermal equilibrium. But because of conductors and insulators, they do not feel the same. It's the same as if you were to leave, like, actually, if you go outside, you grab something metal, like looking outside, I have a ladder against a fence. That wooden fence, and that metal ladder are not going to feel the same at all. The metal ladder is going to be it's going to feel way hotter than the wooden fence, even though they've been in the sun the same amount of time, so they're going to be the same temperature. But the conductor is going to conduct that heat to my hand way faster, even though they're the same temperature. And that's just conduction, not necessarily the fact that they are different temperatures. Now, to get to those temperatures are different, and that is due to something called specific heat. This is represented by a Q, and its equation is Q equals m gat. So we have mass as the m, C, which is specific heat, which is what I'm about to talk about. The change, this little triangle is change in temperature, and then Q, which is heat. So, these are chemistry things. If you're not in chemistry, you'll learn this. If you are in chemistry, or you have done chemistry, you know this. I'm just going to be talking a little bit more about it. So, we're going to talk about another throwing something in water. But we have this thing. We're gonna say it is a piece of wood. Okay. And in this tub of water, we have a piece of aluminum. So, they are two different materials, and though in the end they are going to reach that thermal equilibrium where they are the same temperature, I am an artist and I deserve an art degree. Anyway, though they will reach that same temperature, they will take longer. And the reason for this is because of this thing called specific heat. And the definition of specific heat is how much thermal energy it takes to change 1 gram of something by 1 degree Celsius. So, this object is going to take, metal, like this aluminum. The specific numbers, I have a specific number here. Aluminum is going to take, its specific heat is 0.9. I actually have the exact one right here. So it has a really small one. Because this is lower, it's going to change faster. Actually, this area should be shorter. Because this is lower, it's going to change faster, because it needs less energy to change that temperature. Whereas wood, I don't have the exact one, but I know it's higher. Wood has a higher specific heat, so it is going to take longer to, it's going to take more energy to change its temperature, so it's going to take longer, because it's still water. So this water is going to only provide that same amount of energy for each substance, for each experiment. So like say this one takes 10 minutes, this one may take 15 minutes. And of course, these aren't exact numbers because I didn't do this experiment, but in theory, it would take longer because it has a higher specific heat. So that's how that works. But this video is running quite long, so I'll have to explore some other intricacies of heat some other time. Now I just said that I was going to end this, but I lied. So this is a state change graph, and you will see these in chemistry class, but they are really neat. So here, there is the object is gaining, it's increasing heat. So you're putting heat into the thing, and it is like heat energy, not temperature. Heat and temperature. So this is energy, like you're putting energy into it. And then this is temperature. So it's increasing in temperature, and it's getting an increase in heat and energy. We're just going to kind of ignore this because it's always increasing in energy with this experiment. The temperature is what's different. So here, it's a solid. Cannot read that. Solid. And then here, you would think that it's a solid because it's not changing temperature, but right here is actually where it's melting. And what's weird about this is when it's melting, it looks like it's changing temperature, but it's not, because the ice in that water are still the same temperature, because all the energy being put into that is being used to change the state. So here you have liquid, and it's the same here. So like when you're boiling it, and actually this is normally wacky longer because boiling takes a little bit more energy. So all the energy to change it from a liquid to a gas is being used to change the energy, to change the state, rather than change the temperature. But once it's a gas, all that energy can be focused on changing its temperature. So yeah, just a neat graph that you'll see in chemistry.